You're watching NASA TV.
Hey, good afternoon, everybody. I'm NASA's Dan Hewitt. Welcome to the Johnson Space Center in Houston, Texas. We have some spacewalks coming up on board the International Space Station, where we're going to be installing some new solar arrays, and we're here today to tell you a little bit more about that. I'm joined by some esteemed panelists just to my right, starting off with Dana Weigel. She's the Deputy Manager for NASA's International Space Station program. Just next to her is Dan Hartman, the manager of the Gateway program, here to tell us a little bit about these arrays and their future in NASA's exploration plans. Pooja Jesrani, she is a Spacewalk flight director here at Mission Control Houston at JSC. And then finally, Kieth Johnson, our Spacewalk officer, who will talk us through all the nitty-gritty of the activities. So we will go down the line. We'll start off. I'll hand it over to Dana.
Thanks, Dan. Let's see, it's a busy time as always on board Space Station. We've got 7 crew members up there, 3 NASA crew members, 1 from JAXA, 1 from ESA, and 2 from Roscosmos. The Russians started off the month with the spacewalk on June 2nd. Their primary activity was preparing the Docking Compartment 1, or DC-1, for departure, and that's in preparation for a new module the Russians are launching in mid-July. It's called the MLM, Multi-Purpose Laboratory Module. Crew on board is doing great. They've been looking forward to the SpaceX 22 mission. The logistics associated with this mission are a little bit like a shuttle mission in terms of the activities and the complexity and everything we're trying to fit in during the dock mission. We've got a lot of science that we flew. We've got a couple of deploys out of the GEM airlock, and then of course what we're here to talk about today, we've got 2 upcoming spacewalks to install our new solar arrays. The EVAs will be conducted by Shane Kimbrough and by Thomas Pesquet, and the robotic arm will be operated by Megan MacArthur, and Mark Vandehei will be the backup, helping to operate the arm. SpaceX 22 launched on June 3rd, and it docked on June 5th, carrying with it 7,300 pounds of cargo. Shortly after docking, the crew got to work transferring critical cargo and starting into some of the science experiments. And of course, the ground and the crew have been working really hard to get the EMUs and the tools prepared for these upcoming EVAs. And then last week, we used the robotic arm to extract the carrier that has the arrays on it from the Dragon trunk and got our first look at the solar arrays, and those are in great shape. Let's see, can I get the solar array overview image? Let's see, this one kind of shows the augmented arrays. I think there's another image that shows where the augmented arrays go over it. That's all right, we can use this one. Let's see, we're planning to upgrade 6 of our 8 power channels. The original solar arrays were certified for about 15 years. Of course, nothing magical happens at the 15-year mark, but the arrays do degrade over time. That's to be expected. For us, there are a couple of real factors that affect the degradation. One of those is erosion that we see from thruster plumes. That's both from the station thrusters along with the crew and cargo vehicles that are coming and going. The other factor that affects our solar arrays is micrometeoroid debris. And so the arrays are made of a lot of small power strings, and over time those power strings can degrade if they're hit by debris. And so the new arrays, thank you, the new arrays are installed on top of or in front of the existing solar arrays, and this shot gives a good view of what it looks like to see the new arrays overlaid with the old arrays. The exposed portion of the old arrays will still be generating power in parallel with the new arrays. Those new iROSA arrays have solar cells on them that are more efficient than our original cells. They have a higher energy density, and together, in combination, they generate more power than what our original array, when it was new, did on its own. On the right side of the screen there, those 2 far arrays are called 2B and 4B. Those are the ones that we're going to upgrade during these EVAs. They're on the P6 truss. Those are our oldest set of solar arrays. They're just a little bit over 20 years old. Next image of the iROSA deploy? Not that one, the one where we did the demo off the arm in 2017. All right, that's okay. Go back to that one. We can talk that image. Okay. This is an image of the actual flight array. And so this is a great shot because you can see both the solar cells kind of sectioned along the blanket, and you also get a feel for the size of the array. They're built by DSS, Deployable Space Systems, is the contractor who built it. And then Boeing, our prime contractor, built the carrier, and they also did all of the integration for the array. All right, let's see if we can find that iROSA deployed shot from 2017. Another interesting shot, not that shot, but I'll talk to this one. This is a view of the iROSAs rolled up. They're really unique because the technology allows us to roll them up into very tight tubes. So what you're looking at here is a view in the trunk of the rolled up array, and it's folded in half, and there's actually two sets. You're seeing a really good view of one of the arrays on top, and then if you look at the bottom of the image, you can see the other array set just under it there. Okay, let's see if we got...
And it sounds like we don't have that other shot,
Okay.
so
Let's just
keep rolling.
I'll just talk to it. So back in 2017, we did a demonstration and deployed a test article demonstrating this array technology. That test article was smaller than our station arrays, and we deployed it off of the SSRMS just to test the capability. Our station array is quite a bit bigger, and one other difference is for the ISS demonstration, we needed to retract the array since it wasn't permanently staying with us. Our arrays, on the other hand, are only being deployed. We're not going to retract them, and so we don't have a motor on them. Following the mission, we got a lot of activities going on across the rest of the summer. At the end of June, we will have NG-15 release, and then shortly after that, the Progress 77P will depart with docking compartment 1 in preparation for the MLM, which should arrive sometime in mid-July. And then after that, we'll be doing a Crew 2 Dragon relocation to free up a port for the Boeing OFT-2 vehicle that will plan to launch on July 30th. And so with that, I'll hand it over to Dan Hartman.
Well, do you want to talk about that video while it's playing and,
Yeah, I'm
and
not
talk
sure.
about what was going on?
I think you want to replay it when...
We'll get to that one a little bit later. Dan, why don't we jump over to you now?
All right. Well, thanks, Dana. And honestly, thanks to the ISS program for allowing us to come in and have a discussion about Gateway. As you know, there's a lot of synergies, a lot of lessons learned, a lot of technology demonstrations that we can apply from the International Space Station going forward to the design, development, test, and eventual deployment of the Gateway. And so several of those things are things like the ECLIS system. We're working with the ISS program and JAXA to actually provide a CO2 scrubber. Jointly with the ISS program, we're working on an upgrade to the existing EVA suits. The NASA docking system that'll be tried out here soon with the Boeing vehicle. We're leveraging highly off the NDS, especially the passive systems associated with the docking system. That'll be on our Halo module. And then the fourth example I have is the solar arrays. The solar arrays are built by the same company, DSS, that we plan to use for the Gateway. It's about 60 kW of power that you see in those figures. They're presently doing a lot of strength testing on the booms. As we've seen in the past, solar array management on the International Space Station can be challenging at times with all the visiting vehicles and the pluming effects that come into that. We're taking all those lessons learned into how we're actually designing and managing these two solar arrays that are on the power and propulsion element. And so, we do have gimbaling capability on each one of those arrays. Basically 2 wings and then 2 segments per wing that allows us to generate about 60 kilowatts of power for the Gateway. That power generates everything. That is our power source for the entire Gateway program. We have that power channelized. We move that power to the different modules and to the different elements, and obviously we've allocated some power associated with these arrays for the utilization. We're trying to make sure we take care of our utilization friends, especially early. We got a couple of payloads that are going to be flying up on the PPE and Halo that you see in this figure. But size-wise, the arrays are about the same length as what you'll see deployed here shortly on the ISS program, but ours are wider, and that does give us about 30 kW per wing versus what you have on the ISS. The other major difference is these are completely automated, right? So when we launch PPE Halo as a co-manifested vehicle on the Falcon Heavy, one of the first activities that we do is go deploy these arrays to get power generation. We'll be on battery power up until that time period, but it's completely automated. And so kind of I'll say the poles pop out, then the wings deploy out, then we're in a position to actually go deploy. Again, it'll be very similar to the technology that's used on the International Space Station, and it takes about 30 minutes per solar array to fully deploy. And so obviously, we're going to be watching as the ISS EVA crew members and team go integrate these PPE arrays over the existing ISS arrays and certainly apply any lessons learned that we have there. The other thing we have started actually accepting some of the flight solar power modules, which is I'll say a conglomeration of a bunch of the solar cells, very similar to what you saw on the iROSA. There's about 800 of these modules, and we have received the first 12 actual flight units. And so we're well on our way with generating or designing, developing, and delivering some of the key components for the power and propulsion element. 2 arrays, 15-year life, and like I said, a lot of power for utilization, and then also an extensive amount of power for when we do our solar electric propulsion burns, or not actually burns, but those maneuvers around the moon. It takes a considerable amount of power for the solar electric power system to operate. We know how to power our systems down to allow for that. Most likely those will be done during the uncrewed time periods, and so we're really looking forward to that eventual opportunity. A couple other things associated with the Gateway. We've had a series of preliminary design reviews. The PPE, the power and propulsion element, led by the Glenn Research Center, and Maxar just had their PDR last week. The Halo, which is the module, the pressurized module that Northrop Grumman is building, they had their PDR at the tail end of May. And then we just got back from an ESA trip last week where we had the International HAB preliminary design review. So there's a lot of progress being made across the Gateway. Our first elements are for the PPE and Halo. We're still looking to launch in the late 24 time period, and so we're tracking to that. We are certainly managing to that. As I mentioned earlier, a couple payloads on the outside of PPE and Halo, basically to measure the weather, the space weather in the lunar environment, and we're doing that collaboratively with all the international partners. So CSA, ESA, and JAXA are all participating in those payloads that were flying earlier. And so, like I said, we'll certainly be watching the ISS arrays as they deploy out, taking those into account in our design as we go forward. And Pooja, I'll turn it over to you.
Well, awesome. So I think I'm going to talk a little bit more about the EVAs specifically. So as you guys know, we have these EVAs coming up. The first one's on Wednesday, and the second one is currently scheduled for Sunday. The first one specifically will be the 2B EVA, and we're super excited to be working with Thomas and Shane for these. It's been a very busy year on ISS. We've had this will be our 7th EVA, I should say, and specifically for Shane and Thomas, this will be their 3rd EVA together. They got to do 2 EVAs back in 2017 for battery R&Rs, and so we're excited to see them go out the door again together. Another tidbit that I found out is that this is actually our 239th spacewalk for ISS assembly and maintenance, which I thought was quite impressive. So 239, guys. And here we are again doing another EVA. Specifically, Thomas will be the one in the red stripes, he'll be EV1, and Shane will be EV2 in the unmarked suit. And here again, you can see some of the stats that I mentioned in terms of how many spacewalks they've both accomplished. In terms of iROSAs specifically, as Dana mentioned, we've been working very hard with the DSS team, the Boeing team, and the NASA team, and SpaceX to develop and fly these iROSAs. If we want to go on to the iROSA picture, since the first pair of arrays on the International Space Station were deployed, in the year 2000, the additional arrays since then added up all the way to 2009. So we had 4 sets of pairs, the first again in 2000, all the way to 2009. And these iROSAs that you see here are now going to be providing an additional gain of 30%. After SpaceX 22 docking SpaceX 22 docking earlier this month, we were able to robotically grab the iROSAs from the SpaceX trunk and place it on the mobile transporter. We'll be using that mobile transporter to help move the iROSA wings further out on our work site, all the way out to work site 8, which is the furthest port we'll be able to get to. In this picture that you see here, the iROSAs are actually shown in blue, as you can see, the new solar arrays. And that's actually showing where the iROSAs are all the way out to the mobile transporter worksite 8 position. From there, the EV crew members are actually going to be using that as a worksite and then releasing one of the specific iROSAs. EV1, Thomas, will be flying that over and handing it off to EV2, who will be in an APFR. They'll do their first handoff, and then while EV2 has it in the APFR, he'll be doing a yaw maneuver and then handing it back off to EV1, who will be actually next to the worksite, either 2B or 4B, depending on the EVA. Once they are both at the actual worksite, they'll be installing it onto the mod kits and making sure that it's structurally sound, doing the connectors that are needed for legacy electrical power systems, and then deploying the iROSAs. The deployment for the iROSAs themselves are very interesting. It's actually, instead of motors for deployment, we're actually using stored energy from carbon fiber booms that are cut and rolled back against themselves into a specific shape. So if you actually think about a straw and you cut that lengthwise and you rolled it up, and then if you deployed that straw, it would want to go back into the original shape. That stored strained energy is really what's being used here. That stored strained energy, as well as the magnets on top of that, will be providing that structural interface that we need for these arrays. These new solar arrays, like you can see in this picture, are going to be positioned right in front of the legacy solar arrays. They are 10 degrees canted, and we'll be using the existing sun tracking, power distribution, and channelization of the legacy arrays. This approach is really similar to how we upgraded the station's external cameras as well. For high def, we used existing power and control mechanisms for those as well. As we've already talked about here, these EVAs are quite complex, just like every EVA that we do, with all the bolt ops that we have to do, with all the connectors that we have to do, the mass handling. The iROSAs themselves are 750 pounds, 10 feet long. There's just a lot of work that has gone into these EVAs, and we're really excited to work on this as a team. As you see here on the Spacewalk 74 team is shown here. Again, Thomas and Shane is the EV1 and EV2 crew members. You have Mark and Megan. Mark specifically will be the suit IV. Megan will also be helping with suit IV, but will also be in charge of the robotics. You see Ron Spencer here. He's listed as the flight director for the 2B EVA, and then you have Jenny Seide, who's the ground IV. I am the flight director, as you can see here, for the 4B EVA, which will be happening on Sunday, Spacewalk 75. And so, like I said, it's been a busy few months as we've been getting ready for these EVAs, but we are super excited and prepared and ready to go out the door. And with that, I'll be handing you over to Keith, who is our EVA specialist.
Well, thank you, Pooja. Thank you, everybody. So this crew has done EVAs together before. I happen to be the EVA lead for those particular EVAs, and that's exciting. I've seen how these guys work together, and it was especially encouraging. You saw the video shortly ago of the hardware being prepared at Kennedy Space Center. Our crew got to go and walk around this hardware right before they got ready for their launch on their Crew 2 vehicle. And as they were walking around looking at the hardware, we joined them in COVID times by having a camera follow them along, and we did kind of a Teams call to talk to them about what the hardware was, what the mechanisms were, what to look out for, where sharp edges might be, things they can touch, they can't touch. This video gives you just a really great idea of how big the solar arrays are. It takes a bit to walk around them and see what they look like. The crew is going to be very careful with these when they take them off of the FSE and move them to the worksite. Again, It's 750 pounds, so it's a big mass, and you can see in that picture right there, it's 10 feet long. And so they're holding it from special handling tools that they have at either end, and they hand it off to each other. So this is a really great video that gives you an idea of the preparation and the work it takes to get this ready to launch. Pooja mentioned some of our work sites. I'm going to show you a video shortly of how we move it out. But one of the interesting challenges that we have is a crew member at the end of the arm holding on to iROSA using handling aids that we install. They are worried about the volume that iROSA takes inside of the SpaceX trunk, and so they minimize that by taking handrails off and maximizing the amount of power that they can generate from the solar array. In order to do that, we have to put these handling aids on when it's at the FSE or on where the arm is going to take it off. That's part of the preparation work. But then handling it and getting it out to the other crew member takes a lot of work. It takes the extent of the arm reaching as far as it can go, and they hand it off to the other crew member, to Shane, who's in a foot restraint, and he'll get a hold of it, and he'll just hang on to it. In the meantime, Thomas will exit the arm off the SSRMS, the foot restraint there, and he'll move over and reposition Shane, and then egress that and get into another foot restraint. My video will show how those go into position. Then the two of them will maneuver it onto a mounting bracket. It takes two crew members. There's some alignment guides that are on there that they slide across, and it locks into what we call a soft capture feature, which are pins that pop into place and kind of temporarily hold it. And this is all done prior to deployment. This is just installing it on the mod kit that was installed on previous EVAs. They'll drive some bolts, they'll swing it open, and here you see a long blue tube, and that's the solar array prepared for deployment. We'll hook up some electrical connectors, and then we'll send it out. And I think next, I'm not sure what the next picture is here, but after this, I have a video that we put together. We use our virtual reality lab to put a movie together where they seamlessly flow through the EVA with electronic pictures. And so if you can play that now.
At the start of the EVA, EV1, Thomas Pesquet, comes out first, followed by EV2 Shane Kimbrough. Thomas translates up to the front face of the truss and translates outboard. Thomas is setting up what we refer to as safety tether anchors. At this point, he'll drop the anchor point for both he and Shane. Shane will be retrieving an articulating portable foot restraint and putting his stowage bag onto it for translation outboard. Thomas makes his way out to the carrier that has the solar arrays stowed on it. Shane follows along the truss and meets Thomas at the carrier. The crew drops off pistol grip tools and bags in preparation for releasing iROSA from the carrier. Shane makes his way outboard onto the P6 truss element and stows the articulating portable foot restraint that he'll be using later on in the EVA. Continues translating outboard to the very end of the truss and stows his stowage bag. Thomas prepares the iROSA by releasing the first hinge bolt and stowing his pistol grip tool. Thomas makes his way outboard and releases an anti-rotation device which keeps the primary bolt locked in place during launch loads. Thomas retrieves a handling aid for iROSA. We refer to this as a scoop. Meanwhile, Shane retrieves a crew lock bag and installs it on the lower support truss of the mod kit. He retrieves another scoop, another handling aid, and installs it on the mounting bracket of the mod kit. Shane retrieves one of the two sets of cables and pre-positions them for future installation. Shane retrieves his pistol grip tool and makes his way back inboard to join Thomas. Thomas prepares the release bolts down to the last few turns. Thomas installs one of the handling aids and makes his way back around iROSA. He changes out his pistol grip tool and makes his way down to the crew and equipment translation aid, or CETA cart, and retrieves the foot restraint that he'll use on the end of the arm for his work with iROSA. He installs the foot restraint at the end of the arm, puts it in the right position, and ingresses the arm. The arm then flies him into position to drive two bolts that are on the boom deployment system. Once these bolts have been released, the booms can be moved outboard, and this will help with the release of the solar array when it's eventually deployed. Thomas drives 2 of the outboard launch restraint bolts that hold the tube in place, and the arm maneuvers him for release of iROSA from the carrier. Meanwhile, Shane makes his way over to the carrier and gets into position for release. Shane drives the last few turns on the release bolts, and now the iROSA solar array has been released from the flight support equipment. He installs a handling aid, and Thomas is able to slide iROSA off of the carrier and remove it. Meanwhile, Shane is keeping an eye on the whole system to make sure that iROSA does not come into contact with the RMS grapple fixture, and away Thomas goes with iROSA. Meanwhile, Shane gets off of the carrier and translates outboard. He'll stow Thomas' safety tether hook in preparation for when Thomas comes off of the arm, and he'll continue his path outboard. He stows his pistol grip tool, makes his way to his foot restraint, and ingresses. While he's getting into his foot restraint, Thomas is continuing his path, holding on to iROSA while the arm flies him as far outboard as it can reach. He hands off the iROSA to Shane. They swap tethers. Shane has control of iROSA and is left holding it, while Thomas goes back to his egress position. He gets out of the arm, changes his safety tether, and makes his way back to where Shane is holding iROSA. He then rotates Shane into position so that iROSA is handed off to the next point. Thomas ingresses his foot restraint and receives iROSA. Shane egresses his foot restraint, moves outboard, and gets into position to help Thomas install iROSA onto its final location on the mod kit. One of the 2 handling aids is removed before installing onto this mounting bracket. The 2 crew members work together to align it and put it into a soft capture feature. Once it's installed, the other handling aid is removed, the final hinge restraint bolt is loosened, and iROSA is now able to rotate into its fully deployed, fully extended position. The 2 crew members work together to swing it into the single tube. Once it is in position, Shane stows the 2 handling aids. Thomas gets into position to drive the hinge bolts. These 2 bolts hold the 2 halves of the iROSA solar array into a single tube. These bolts are delicate pins, so the final torque to get them into position is done with a hand tool so that we don't over-torque those bolts. Once that's in place, there are 8 mounting bolts that hold all of the iROSA solar array onto the mounting bracket. Thomas will drive the first 4, followed by Shane driving the second set of 4. Shane and Thomas will work together to install the electrical cables that hook up to iROSA. One set goes to the right side and the other set goes to the left side, and they are finally hooked up in place on the legacy solar arrays. That's done during eclipse. After those cables are installed, the crew gets into position to drive the final 2 bolts that are holding iROSA in the pre-deployed position. Once these 2 bolts have been driven, iROSA is free to extend itself into its deployed position. After the crew's verified that the solar array is in the right position and it's fully deployed, they drive 2 tensioning bolts. This allows the sail to be tensioned into its final configuration. Once iROSA has been fully deployed, there are some checkout steps that are performed to make sure that everything is hooked up correctly, and the crew cleans up the worksite. They retrieve the handling aids and the pistol grip tools, and they prepare for the second EVA in the series. To do this, they take their foot restraints and move them to the other side of the P6 truss structure. This will be the worksite for the second EVA. Each crew member has their own foot restraint, and they'll move them to the other side. The crew repositions the stowage bag that's holding the other set of cables to the other side of the truss, pre-positions it for the next EVA. The crew will do an inventory of all their tools and their hardware, and they'll start their path back to the airlock. On their way back, they'll stop at the carrier, pick up the last crew lock bag and the last pistol grip tool, and make their way inboard. When both crew members are back at the airlock, they'll retrieve a foot restraint that has been causing us problems and bring it inside the airlock to inspect. Shane will enter the airlock, followed by Thomas, and that ends the first EVA.
His only question.
All right, back to you, Keith.
Okay, thank you. So yeah, this crew had a chance to see the majority of what it takes to do this EVA in our neutral buoyancy lab. So they got to practice together, but only a few times. So the way we do business now with International Space Station training, they get a few chances to see what would normally, back in the shuttle days, they had many runs of this kind of an EVA. So we're kind of counting on them studying their procedures and asking us some of the detailed questions it takes to get ready for an EVA. Some of the contingency tasks they may be asked to do. If it doesn't go smoothly, we hope it all goes smoothly. So from that standpoint, we're excited to get the crew ready, get them out the door early Wednesday morning. Before I hand it over to you, Dan, I have something else important that I'd like to say. Several years ago, I had a chance to tell each of these two women here, I gave them some advice, some career advice. I said to Dana, I said, you should try and be a flight director. And she looked at me and said, you know what, I may go do that. And Pooja, a couple of years ago, I said the same thing to Pooja. I looked at her and I said, you know what, you'd make a good flight director. And I am so pleased to work with both of these women, and Dan, you too. But it really is kind of unique to be sitting here with them, and I feel kind of honored that I'm the one that maybe helped them with their career advice. So.
Thanks, Keith. Absolutely, Keith. I agree.
All right.
Thank you.
And now they're both your boss. All right, cool. Thank you, Keith. All right, so a couple of quick housekeeping items. So thank you for all of our opening remarks. We're going to get into questions now. We are still virtual, so if you're media and you're on the phone bridge, use the *1 to get into the queue, *2 to get out of the queue if your question has already been answered. And I should have said it at the top, but we're all in the room together. We're all vaccinated, so that's why you see us without masks today. So get vaccinated. All right, so we will start with questions on the phone bridge. We're also taking questions on social media. You can go on Twitter, use the hashtag #AskNASA. All right, and so for our media guests, again, please tell us who the question is for as you're asking it. We'll try to keep it to one, but I think we do have a little bit of time, so if you have follow-ups, we'll get to them. All right, we will start off with Bill Harwood from CBS News. Bill, can you hear us?
Yeah, I hear you loud and clear. Thank you very much. A quick question for Dana. You know, a lot of folks were intrigued by that recent photo we saw of a debris impact on the SSRMS. I doubt the numbers have changed, really, but the picture kind of brought that back to light. I was just wondering if you could talk a little bit about the debris risk for an EVA and how you guys assess that these days. Thanks.
Yeah, it's a great question, Bill. As you guys know, we live in an environment in low Earth orbit where we frequently have micrometeoroid debris. In some cases, it's of a trackable size, and I think you're aware, but we make specific decisions based on the likelihood or the risk that it'll approach ISS or could contact ISS. And so for larger items, we'll maneuver out of the way if we think the risk is high enough. But there is a bit of background debris that's out there. In fact, what hit the arm, even though the image you see a lot of damage to the outer layer of the blanket, so it looks larger, but the actual impact spot was very small, and what went through the arm was actually a pretty small piece of debris. So that's always a challenge for us, traveling with debris. Space station itself is shielded to a certain level. For example, on the U.S. segment, we can handle strikes without any damage up to 1 centimeter. I don't know the number off the top of my head for the EMU, but it's also got some protection on the soft goods. The other interesting thing is that the EV crew they're really close to structure, right? So they're maneuvering around and in and out of structure, and so that also offers them some protection. But similarly to what we do with space station, if we see debris that's trackable and if we have an EVA, we can make decisions like delaying the EVA or if we had to actually maneuver the vehicle out of the way. So it's a similar method that we use for tracking and monitoring the debris environment.
All right. Thank you, Dana. Next up, we have Marcia Dunn, Associated Press. Marcia.
Yes, hi. Probably for Keith, could you address how you're going to protect the spacewalkers from any shock hazards, electrical issues working so close to solar panels, and when the new panels are actually unfurled, extended, do the astronauts have any role in that whatsoever, or is it totally automated with the natural force? Thanks.
Well, in preparation for an EVA, we look at what's called the plasma forecast, and we determine what kind of electrical charge the space station could be in. We take mitigating steps, like we cover up metallic interfaces on the suit to make sure that there's no metal contact. We put what are called inhibits in place. We turn power systems down, off, We also, when we do electrical connectors, they have what are called, they have special features where the pins are retracted and held out of the way. So when we disconnect, we keep metal objects away, and they're sunken back enough so that it protects them. But the big problem is that we've got giant solar arrays that will be generating power when we're in daylight. And we are disconnecting one of those cables that, if we were in daylight, would be sending a lot of power through it. And so because of that, we plan our EVAs and we time it so that when they get to that electrical connector, we do it at night. And we make sure it's not generating any power whatsoever. We disconnect and mate it back with our, what we call a Y harness, where it's the cable that's going to be combining the power from iROSA and shunting the legacy solar array and providing that power to the rest of the space station. We do that in nighttime and to make sure that there's no power. Let's see, what was the second question? Do you mind if I have that? Is she still there?
Yeah, Marcia, are you still there? Can you give us the second part?
If you can hear me, when the new panels are actually unfurled, do the astronauts have any role in that whatsoever, or does it just pop out quickly on its own?
It's funny because we were just talking about that when we were watching the video. So the crew members are the final release of the pent-up energy of the booms. And Pooja had a really great way of putting what that energy release is, what those stored up fiberglass or carbon fiber booms do. But really what ends up happening, it's like letting the horse out of the gate. So they drive one bolt, and when it's cleared, they move over to the second bolt, and those are the last two bolts holding the solar array in place. And once that bolt is fully driven out, all that energy is going to push the solar array boom out and away. Now they have special, they're not really brakes, but they're rollers that are at the end of the solar array that kind of keep it in a little bit of tension as it's deploying, so that it goes at a certain pace. They've done a lot of testing on the ground. They did, Dana was going to show you a picture of a test article that we flew on space station that has this technology that pushes these booms out at a certain pace. So all they do is they let it go and then they watch. And the interesting thing about that is that this solar array, the area that we want to watch, is facing the old legacy solar array. So the guys in space station, all of our cameras won't be the ones that get to see this boom forming its tube as it's being deployed. It's going to be Shane Kimbrough with his high-def camera image on his helmet that'll be showing us this boom being deployed. After Thomas drives that bolt, he's going to move into position to watch the other side, so hopefully we'll get two images of these booms being deployed.
Yeah, and just to add to what you just mentioned, Keith, the deploy itself is going to take about 6 minutes, so it's going to be a very interesting 6 minutes as we sit in mission control and watch this whole thing happen.
And we're going to make sure we have signal so everybody else can watch too.
Absolutely.
All right. All right, so next up on the phone bridge, we have Mark Carreau, Aviation Week. Mark, are you there?
Yes, thank you. My question is when the next two sets of iROSAs are planned to be launched.
That's you.
Dana, I think we can give just general idea.
They were looking at me. We're still looking at that. We have a couple of trades we're still making through our SpaceX 26-27 timeframe, so we've got some flexibility. As you heard before, we're replacing our oldest arrays here, so in terms of vehicle needs, we've got a lot of flexibility and we can wait a bit longer before we replace our next sets. And so we are working with some other folks in payload customer needs for the trunks to really balance that and decide when we want to launch the next set.
So we'll let you know, Mark.
Yeah.
All right. So let's take a couple on social media. Again, if you want, jump over to Twitter, use the hashtag AskNASA. This first one, I'm going to give this one to Keith from Amir. How are suit temperatures regulated for these spacewalkers?
Well, the suit has, and you know what's funny? You have a suit right here. And I would love to walk, can I walk over and get it?
Let's just
to answer the question. Just answer it?
Just answer.
Well, you got a suit right there. I could point it. Yeah. So, and actually, Dana used to be a spacewalk flight controller as well before she was a flight director, and she knows how the suit works as well. But bottom line is, it's got a temperature control valve on the front, and it's a little turn knob that you can see is written backwards with all of its text on there, and that's because the crew member can't see it when he's looking down at it, so he has a mirror to see what his temperature is, and it goes from a high of the coldest all the way down to a max hot, which is no flow. And what ends up happening is they have a water plate in the back of the suit that they push water through that goes to vacuum, and when it goes to vacuum, it sublimates off, and that sublimation of that water cools off the water flow that goes past their liquid cooling ventilation garment. So by controlling that valve on the front of the suit, they can make it colder or hotter, or warmer, I should say. They just stop the cooling flow when they do that, and that's how they control the temperature. So sorry, I didn't mean to get up and walk over to the suit, but I thought you got a great prop right there, which really might help you out.
Thank you, Dana, too, for the assist. So this next one...
My own Vanna White.
This next one is for Dana, and he touched on this a little bit early on, but SpaceX fan on Twitter wants to know, why do we need more solar panels, or the current ones wearing down?
Good question. So I mentioned previously that the original solar arrays were certified for 15 years of life, and though they're still working, they do degrade over time, and so we get a little bit of erosion from thruster plumes, and just the environmental exposure gets old, not unlike major systems in your home that at some point, degrade or you have to replace. I'd say the degradation rate, if I had to pick a ballpark number, of course it depends how many visiting vehicles we have and what the specific environment is probably about 1.5% per year is probably a kind of a good number to think about there. And so they do start to lose power generation capability. This pair that we're replacing in these next two EVAs is quite a bit older than the others, just because it was launched so early, a little more than 20 years. But to speak to why do we want to replace them and upgrade them, there are a lot of things that we are doing on Space Station. Of course, we're always testing new capabilities, pushing what we can do with science. We have a lot of science that flies to the vehicle. Dan Hartman also talked a little bit about technology demonstrations, and one of the things that's really important with Space Station is trying to use it as a test bed for future programs and future capabilities. The microgravity environment is really unique and presents unique challenges, especially for systems like life support systems that have fluids moving through them. Those behave quite a bit differently in a microgravity environment. So we are flying and building a lot of exploration-grade life support equipment, and it takes quite a bit of power to run that in addition to running our normal life support systems, and so we really want to be able to maximize the use of Space Station. The other thing that's coming along that we'll want to use power for is the Axiom module. So if you recall, I think it was about a year and a half ago, we signed a contract with Axiom to fly a commercial module up to ISS, and that'll need a little bit of power. So there are a lot of things that would benefit from having more power.
All right, thank you, Dana. And another one for you real quick, kind of in the same. So Kate on Twitter wanted to know, how long will the new solar panels last?
So the new solar panels will have a similar kind of 15-year-ish life, but I think, what we've learned with our original set of arrays, we actually thought the degradation would be quite a bit worse than what we actually saw. And so it took us a number of years, and we have a way to test the arrays, to challenge them and test how much power they're generating. And so part of that answer is we've got a prediction, but we'll really need to just start using them and try to learn over time what the degradation is. But we should easily have another 15 years. And again, the degradation is slow over time. It's not an immediate cliff that we fall off of.
All right, thank you. And we still have some more time, so if anybody does have more questions, again, jump on Twitter, use the hashtag AskNASA. It does look like we had a follow-up in the media queue, so why don't we go to Bill Harwood with CBS News one more time. Bill?
Hey, thanks. This is ignorance on my part, but do both sides of the array deploy simultaneously? And what happens if something does hang up, if something doesn't get released? I mean, I know you can't retract it, but could you live with a partially deployed array long-term structurally, or is something else, hung up like that? And I have a real quick follow-up if I have time.
Well, first of all, when we drive the two bolts, you saw that there were two halves of the solar array that folded, and we drive some bolts to make it a single tube. When we release that, it all goes at the same time and goes up. So they are supposed to be equal tension on both sides, and they're supposed to go up, exactly as we see it. But we do not have any planned contingency workarounds to fix anything just yet. But NASA, if something happens, we're gonna stop and look at where it is. We're gonna take pictures. We're gonna analyze what's going on, and we'll come up with a plan to fix it. You've seen us do it before, so we trust that this is gonna do what it's supposed to do. But again, we can react if it doesn't go quite the way we had hoped.
Yeah, and just to add to what you mentioned, Keith, I think in a partial deploy scenario, I think the thing that we're really going to be looking at is thermal cycles. We know that in this case, if, through thermal cycles specifically, that stuck specific array could come unhinged and get us in a better configuration. We have looked at loads constraints specifically with these arrays in a partially deployed configuration, and we do know that we are able to do all of our dynamic events going forward in a partially deployed configuration. We will have to use specific array angles going forward for those configurations if needed, based on our loads constraints, but we know that we are in a safe and good config for all ISS dynamic events in the case that we get it in a partial deployed configuration.
All right. Thank you, Pooja. And yeah, Bill, if you had a follow-up, go for it.
Yeah, thanks. And it's just back to Dana again. Just a real quick follow-up on space debris and EVAs. I mean, I know there's no number for something like this, but how risky do you view an EVA from a debris standpoint? I mean, obviously, anybody in space, there's lots of risk you deal with on a daily basis, but I don't really have a sense of where EVA stands in that risk hierarchy. If there's anything you can say, I'd appreciate it. Thanks.
Yeah, we can get you, I don't know off the top of my head, if you're talking about like probabilistic assessments. The way we manage this programmatically, both for the EMU and also our modules, is we design to a probability of no penetration, a number that will allow us to safely react for the vast majority of the types of debris we would encounter. And again, if it's large enough, we move out of the way. So we can get you the specific numbers for the EMU, but just to mention, for the EMU specifically, it can handle up to a certain size hole in the EMU. There's an emergency oxygen package that will give the crew members about 30 minutes of time for strikes up to a certain size. And so the way we kind of balance that risk is through making sure that we've got contingency plans to deal with bringing a crew member in if there is a strike. And then, of course, if for whatever reason the environment is off nominal, whether that be trackable debris or someone had an unexpected satellite breakup, which sometimes that happens, then we react accordingly and decide if the background environment's too high to go do a spacewalk. But we can follow up with the specific probabilistic numbers.
Okay. And we've got another one in the media queue, Marcia Dunn from Associated Press once more. Marcia?
Yes, hi, thanks. For Keith, when the astronauts are handling that package of arrays before it becomes a single tube, what are the dimensions? I think it's 10 feet, obviously, but how wide across is it when it's all rolled up like that at the beginning? And if there was a partial deploy, are these designed for the astronauts to maybe grab one end and try to tug it loose? Could they do that? Thanks.
To start with, when you saw the video of them walking around iROSA at Kennedy Space Center, the base is about 4 feet wide when it's folded up, rolled up, and it's about 2.5 feet thick, and then 10 feet long. And they hold at either end. There's handrails at one end, and at the other we install special handling aids. So the interesting thing about that is when you're looking at a 2-foot by 4-foot tube in front of you, you don't really have a lot of visibility to see anything else. So they really kind of count on communicating between the two crew members, maneuvering this into position. You know, we got a chance to look at all of it in a tube, rolled up, folded up, ready to go for deploy, but we have not had a chance to go look at the hardware when it's being built and when they're doing their practice deploy. So we just get video images of what that looks like. The experts and the people that built the hardware are the ones that we would count on if something went wrong to help us decide where we can, how close we can get to different parts, and if we would need a tool to poke at it, and what good it would do to even try to do some of those things. So unfortunately, again, we don't have any plans, but we hope that the experts are available to help us build a plan if something goes wrong. And the good news is that we plan these EVAs very close together, which is kind of unusual for a space station as well. And because of that, we're hoping they go smoothly for the first EVA. We take a couple days and it goes smoothly for the second EVA. But what we're hoping is if something goes wrong with that first array, we have some time to turn back around quickly and get back out there and finish up with whatever goes wrong, so that we preserve the time to do the 4B array, Pooja's EVA, soon after. So that's kind of our goal with that.
Yeah, and just some additional details in terms of the size of iROSA specifically once it's deployed. So as Kieth already said, it's 10 feet when it's together, and when we actually open it up, it'll be 20 feet across the board, and then when it's actually deployed, it's going to be about 63 feet long. And to compare that to our Heritage Solar Array is actually 115 feet long.
All right. I think we have time. I've got two more Ask NASA questions I wanted to get through. First one from Robert Perlman. So if everything goes to plan, I'm going to give this one to Pooja. If everything goes to plan with the first iROSA deploy and Shane and Thomas run ahead of schedule, is there a possibility that there's enough time to position and deploy the second iROSA? If not, what are our get-aheads?
Yeah, really good question. I think, you know, with these two EVAs being so close together and back-to-back, we have been talking that exact timeline. We know at this point that there is not enough time to do both the 2B and the 4B EVA and deployment all together in one EVA. In terms of the get-aheads for 2B, if they do get ahead, the crew will actually be assisting with any of the pre-positioning we can do for the 4B EVA. So loosening any of the bolts, specifically on the FSE, which is the flight support equipment that'll be on the MT, and getting it ready so that when we go out the door for the 4B EVA, it'll just be 2 bolts, and then we can grab it and get in position to actually put that in place. Another thing to mention that's different between the 2B and the 4B arrays are that we actually have to be at different port solar array angles, and to do that changes the timeline of the EVA, and so with that as well, we're not able to do both of the two iROSA EVAs in one timeline if we needed to, or could do.
And to help out with that also is we may be the victim of our own success on the first EVA. So in getting done smoothly and getting done in a timely manner, our get-ahead is to get ready for Pooja's EVA. But what that means is then she has less of the nominal task to do on her EVA, and we have to have a list of all kinds of other fun stuff to do to keep to get EVA work done outside with the crew, because they're efficient crew members, and once we send them out the door, we want to keep them busy. We want to get all the other things done that are on our list. So we call those get-aheads. And
we're currently working through that full list to make sure we have our arms wrapped around it, specifically for the 4B EVA, because like I said, for the 2B EVA, our get-aheads will be to get ready for the 4B EVA.
All right. One more quick question, and I'm going to give this to Pooja also, because I know she wanted as many as possible this briefing. Why did we not directly move, this is from Raphael on Twitter, why did we not directly move the panels from the trunk out to the worksite using Canadarm2?
To be honest, the arm cannot reach all the way out there, right? And so we've actually pre-positioned these specific arrays on top of the mobile transporter that are going to help us take it as far out as we can to worksite 8 for the mobile transporter, and then we're going to have our EVA crew members come out and do these specific handoff 1 and 2, like Kieth talked about in the video, to get it all the way out to the port 6 worksite. The arm cannot get us that far, and especially with all this equipment, it's not possible. And so the EVA team has been working this for a handful of years now to make sure that the choreography for these EVAs are good, and we're able to do it like we have planned.
And just to add to that, there are no robotic interfaces on iROSA. as part of this deploy. And I know Dan mentioned on the upcoming ones, they're going to do a lot of this as a mechanized deployment type of a thing, and that has a lot more challenges. You don't have humans in the loop that can stop and look at something and give you an idea of what an issue is. The next set of iROSAs that are going up, that Dana got asked the question of when those iROSAs go up, those are more inboard. So the interesting challenge with those is we may have a crew member on the arm that removes it off of the flight support equipment and flies it directly out to the solar array, and that'll save a lot of handoffs. It's got its own unique challenges to do it that way, and we will be using the robotic arm as much as we can for that case. This one is just so far out there, it doesn't do you any good.
All right. Well, thank you, Keith. Thank you, Pooja. Thank you, Dana. Thank you, Dan. That's going to do it for us for now. So again, we have 2 spacewalks coming up. We're going to be bringing you live coverage as we do with every dynamic event on board the space station. That first one's coming up this Wednesday. If you're in the U.S., it's an early morning, so wake up with us. Coverage begins at 6:30 a.m. Eastern Time, with the spacewalk itself scheduled to start right around 8 a.m. Coverage time will be the exact same on the 20th. Our 2 spacewalkers, Thomas Pesquet and Shane Kimbrough, doing both of these. So you can watch live on NASA TV and at nasa.gov/live. We'll be bringing you live updates across all of our different social media channels as well. So thanks one final time to my briefers, for everybody for asking your questions today. Tune into those spacewalks a little bit later this week. And that'll do it for us here at the Johnson Space Center. Thanks, and have a great rest of your day.